In this video, we're looking at a problem that's mostly a graph interpretation problem. And the context here is that we're told we have a set of velocity time data for a block sliding to a stop. So this looks very much like the data we would collect with position sensors in the lab. So we're going to use this data to find the acceleration of the block, and then we'll use that acceleration to solve a dynamics problem where we find the coefficient of kinetic friction for this block by observing this sliding to a stop. So we collect the data, and that's all the little cyan dots in this graph. And then we use our software to compute a best fit line to this data, and it just automatically spits out a slope for this best fit line. And that's given right here as negative 1.78 meters per second, which is the same thing as meters per second squared. We also use the software to get the area under this best fit line, and that turns out to be 0.57 meters. And we've also marked on the graph the initial velocity of 1.424 meters per second. Now this actually all amounts to more information than we need to solve the dynamics problem in part B, but just as a graph interpretation issue in part A, we're asked to write down the acceleration and displacement for the block. And this is a velocity time graph, and the slope of that gives you the acceleration. So I can say the signed acceleration here is negative 1.78 meters per second squared. And that just means if the block is sliding to the right and we call that the positive direction, the acceleration must point the other way, it's pointing to the left. Now our displacement, delta x, displacement is given by the area under a velocity time graph. And again, this was just computed for us in the software, and it turned out to be 0.57 meters. So that's how far this block was sliding before it finally stopped. Now in part B, we get into finding the coefficient of kinetic friction for the block. And this is where we realize we've been given more information than we actually need. One approach to this problem is to use the initial velocity of 1.424 and the displacement, or the total sliding distance. And then you can solve a kinematics problem, but the point of that problem is to find the acceleration, which we've already computed in the software. So we're just going to use this acceleration right from the beginning. So to begin the dynamics problem, we'll go ahead and bring in a picture of this block. So there's the block shown sliding to the right and slowing down, so the acceleration is going to point to the left. And we've already put all the force vectors into the diagram. So those force vectors are the weight of the block mg pointing down, the normal force pointing up, which also has a magnitude of mg in this case because there are no other vertical forces tampering with this problem. And then here's the cause of the block slowing down. That's the kinetic friction force pointing opposite the direction of the slipping. And that's going to induce our leftward acceleration in this problem. So rather than calling the acceleration negative and the kinetic friction force negative, let's just use leftward as the positive direction for the analysis here. And we write down Newton's second law. So there it is, F net equals ma, and we're analyzing the x direction here, so we can actually subscript this just to make that really clear. Now the net force in the x direction, there's only one of them, and that's our kinetic friction force. Next, we can put in our kinetic friction formula. The kinetic friction force is given by our coefficient of kinetic friction, mu k, times the normal force, which we know is mg. And the m's are going to cancel out here, so we never needed to know what the mass was to make this work. Finally, we can solve for the kinetic friction coefficient, and that's going to be a over g. And again, we chose a coordinate system where we could just talk about a as a positive number. So I can put in my 1.78 for a, and the usual approximation of 9.8 meters per second squared for g. And when we run the numbers on this to 3 significant digits, we get a friction coefficient of 0.182, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.